Welcome, focused learners, to the Ultimate Exam Mastery Explainer. Today, we're not just reading textbooks, we are cracking open the examiner's playbook for Cambridge Computer Science. Whether you're sitting for syllabus 0417, 0478, 2210, or 9618, the challenge is exactly the same. You see, mastering this subject isn't just about memorizing hardware and software definitions. It requires bold strokes of analytical creativity backed by a rock-solid structural foundation. To show you what I mean, let's look at two completely different types of students we see in the exam data all the time. First, there's Alex. Alex is a walking encyclopedia. When Alex sees a question, they overload the page with raw, unfiltered computer science facts, pouring out every single thing they know, but with absolutely zero analysis. It's a massive brain dump. Then, on the other end of the spectrum, there's Sam. Sam gets nervous about the clock, rushes through the paper, and completely misses the specific command word requirements. Sam ends up answering the question they wish they were asked rather than the one actually printed on the paper. Today we're going to look at their flawed answers, literally look at the red pen marks and discover exactly how to transform them into top-tier responses using clear knowledge backed by a proven exam strategy. You ready? Let's dive into this.
Here is our strategic roadmap for today's session. We'll start with software system essentials, move into operating systems decoded, tackle the complexities of interrupts and buffers, break down languages in translators, and finish strong with ultimate exam answer strategies.
All right, let's jump right into Section 1, Software Systems Essentials. To get those high marks, we have to draw a hard, undeniable line between the two main categories of software. System software is the foundational layer. Think of it as the concrete foundation and plumbing of a house. It runs constantly in the background to manage your actual hardware. It provides a stable platform on which all other software can run properly, and crucially, it provides the human-computer interface, or the HCI. On the flip side, application software is like the furniture in the house. It allows you, the user, to actually perform specific, real-world tasks. Think of using a spreadsheet to model financial data, or a word processor to type out a history essay. Now, when students like our archetype Alex answer a question about software types, they usually just list off apps. They write, oh, system software is Windows, and application software is Word, Excel, and video games. But the examiner doesn't want a list of brand names. They want the structural definition. System software controls and manages the allocation of hardware resources. Application software meets the specific functional requirements of the user. That is the distinction you must make.
Now, take a really close look at how system software branches out into crucial subcategories. It's a whole family of tools. You have your operating systems, obviously, doing the heavy lifting, but then you also have device drivers. These are tiny pieces of software that translate instructions so your hardware devices, like a brand new printer, a graphics card, or a USB stick, can communicate effectively with the operating system without crashing. Then you have utilities, which are your housekeeping programs. They help manage, maintain, and control computer resources. We're talking about virus checkers, disk defragmenters, and backup software. And finally, you have translators, like compilers and linkers, which we'll discuss deeply later. The takeaway here is that if an exam asks you to identify system software, you need to pull from this exact tree. It's not just generic background noise, it is a highly specific suite of programs absolutely vital for allowing the hardware to function at all.
Moving on to Section 2, Operating Systems Decoded. Let's look at the ultimate manager.
Look at this diagram. A typical operating system handles a massive web of background functions. It's juggling everything from human-computer interfaces and multitasking to user accounts and error handling. But how do you write about this in an exam without sounding like a disorganized mess? This is where we introduce the Ultimate Computer Science Success Blueprint, the PEO framework. That stands for Point, Evidence, Explanation, and Link. If an examiner asks you to describe an OS function, like security management, you don't just say it keeps you safe. No. Your point is that it ensures the integrity and confidentiality of data. Your evidence is that it oversees software updates and maintains user access rights. Your explanation details how it uses multi-access hierarchy levels, like passwords and biometric scans, to restrict data access. And finally, you link it back to the question by stating this prevents unauthorized system changes. Before we continue, subscribe to our YouTube channel Ace the Exams, @acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so using PEO is exactly how you turn a jumble of raw facts into a bold, top-tier answer that examiners absolutely love to read.
So,
Let's see how Cambridge actually tests this on paper. Here's a real sample exam question asking you to contrast two types of human-computer interfaces. It reads, explain the difference between WIMP and post-WIMP interfaces. Now, this is exactly where our rusher Sam usually trips up and loses marks. Sam sees the word WIMP, gets super excited that they remember the acronym, and just starts writing down what it stands for as fast as possible. But look closely at the command word on the screen. It says, explain. Let's set a mental timer for 30 seconds and see if you can spot which of the following answers actually explains the difference.
All right, time's up. Let's look at the breakdown. The high-level answer explicitly contrasts the pointing device of a WIMP environment, which, yes, stands for Windows, Icons, Menu, and Pointing Device, with the tactile pinch and rotate touchscreen actions of a post-WIMP environment. Now look at Sam's low-level answer with all the red pen marks. Sam wrote, WIMP means Windows, Icons, Mouse, and Pointer. Post-WIMP refers to tablets. Do you see the problem? This completely misses the functional difference. The high-level answer secures maximum marks because it actively explains that a user doesn't even need a pointing device in a post-WIMP environment. They simply use their finger or a stylus for physical movements like pinching, swiping, and rotating, which are fundamentally impossible to do with a standard computer mouse. It shows a deep understanding of how the user interacts, not just an ability to memorize acronyms.
The crucial examiner tip here is command word decoding. If the question says explain, you have a duty to actively compare the interfaces and detail the why and the how. You cannot, under any circumstances, just list what an acronym stands for. You have to paint the full picture, provide the structural context, and explain the actual real-world differences.
Let's transition into Section 3, Interrupts and Buffers. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's look at how the CPU handles completely unexpected events. I want you to imagine you are printing a massive 100-page assignment, and suddenly your printer runs out of paper. The printer needs to tell the computer to stop sending data right now, otherwise that data will just be lost. So it sends an interrupt signal to the CPU to demand immediate attention. An interrupt is essentially a high-priority signal sent from a hardware device, from a piece of software, or even from an internal clock, directly to the microprocessor. It tells the microprocessor, hey, temporarily pause your current task right now because you need to service this new, extremely urgent request.
If you were asked to describe this process, this 4-step sequence is your ultimate cheat sheet. First, the interrupt signal is physically received by the microprocessor. Second, the microprocessor temporarily pauses its existing task and saves its current state. Third, and listen closely because this is where you get the highest marks. The interrupt is serviced based on priority using an interrupt service routine, or ISR. You absolutely must use that exact terminology, interrupt service routine. If you just say the computer fixes it, you get 0 marks. And finally, step 4. The original task state is restored, and the CPU resumes what it was doing once the interrupt clears. Now, buffers play a huge role here too. Buffers are temporary memory holding areas. While the CPU empties the buffer's contents to a slow printer, the CPU can carry on with other faster tasks. Once the buffer is entirely empty, the printer sends an interrupt asking for more data. It's a beautifully structured, highly efficient dance between fast processing and slow hardware.
Knowing the definition is great, but memorizing these specific triggers will give you the exact vocabulary examiners are looking for when they ask why an interrupt might occur. It could be a software error, like a program attempting a mathematically impossible divide by zero operation. It could be a hardware fault, like that paper jam we just talked about. It could be a timing signal error, where internal operations suddenly fall out of sync. It could be a standard input-output request, like a hard disk drive requesting a block of data. Or it could be as simple as user interaction, like you pressing a key on the keyboard or clicking your mouse. Whenever you are asked for examples of interrupts, pull directly from these specific categories.
We are now entering Section 4, Languages and Translators. Time for an interactive workshop. Welcome to Challenge Number 1, the data scan. You have a mental 60-second timer. Look at this complex comparison table between high-level and low-level languages and extract the core trend. What is the fundamental trade-off here? Well, high-level languages like Python, Java, or C++ are much easier for us humans to read, write, and debug. They use English-like statements.
And most importantly, they are hardware independent, meaning a Python script written on a Mac can generally run on a Windows machine. But low-level assembly languages are an entirely different beast. Low-level languages are essential when a programmer needs lightning-fast execution, code that takes up virtually zero memory space, or direct granular control over specific hardware components like a graphics processor. So the core trend you need to extract is this: you are always trading human ease of use for absolute machine-level execution speed. Moving to challenge number 2, find the flaw. I'm going to read you a thought process from our student archetype, Sam, and I want you to find the sentence that loses all the marks. Ready? Sam writes, "Because computers only understand binary, we use translators. Compilers translate high-level languages line by line, which is great for distribution. Interpreters process the whole program at once." Okay, did you spot the flaw? Sam has it completely backward. Compilers process the entire program all at once in one big batch to produce a final executable machine code file. This is perfect for distributing commercial software because the end user doesn't need the original source code. Interpreters, on the other hand, translate high-level languages line by line, executing each statement immediately before moving to the next one. This makes interpreters absolutely perfect for debugging during the development phase, because execution stops the exact moment an error is found, and an error message is immediately output to the programmer.
Let's tackle challenge number 3, speed writing. You need to write a perfect paragraph on integrated development environments, or IDEs. To write code efficiently, programmers use an IDE, which acts as a powerful all-in-one workshop. Let's apply our PEL framework. Your point: an IDE speeds up software development. Your evidence: it bundles tools like a smart code editor, a runtime debugger, and auto-completion into a single application. Your explanation: instead of using a basic text editor and then manually running a separate translator in the command line, the IDE provides context-sensitive prompts, highlights syntax errors in red as you type, and lets you step through your code line by line using breakpoints to inspect variables. And finally, your link. This comprehensive, unified toolset prevents logic errors early on and dramatically reduces the time it takes to get a working, bug-free program out to the market. Boom! Full marks in under 60 seconds.
And finally, Section 5, Exam Answer Strategies. Let's bring all this theory together into the final system.
Here is a classic, heavily weighted exam question targeting your knowledge of translation programs. It says, identify 2 different types of high-level language translation programs and describe the difference between them. Notice how the question has 2 distinct parts. Rule number 1 of our system is command word decoding. Identify means you just need to accurately name the programs. Describe means you need to state their characteristics and explicitly compare how they function. Let's look at how our students handled this.
The high-level answer on the left correctly identifies compiler and interpreter for the first part. Then it perfectly describes the difference. A compiler translates the whole source code at once and produces a standalone executable file, whereas an interpreter translates each statement and executes it immediately before moving to the next. Now look at the low-level answer on the right. Sam completely panics and writes PyCharm and idle for the identifying part. Sam completely loses the mark by confusing IDE software suites with the actual underlying translation utility running inside them. PyCharm is an IDE. Yes, it contains or utilizes a translator, but it is not the translator itself. Precision in your terminology is literally the difference between an A star and a B.
Always align your answer directly with the command word. And remember that sloppy terminology can cost you incredibly easy points. If the concept is user account management, do not write user account manager. It sounds like a tiny difference, but to a Cambridge examiner, it shows a lack of precise technical vocabulary.
So here's the final system that guarantees top marks. Number 1, command word decoding. Answer exactly what is asked. Number 2, PEL framework application. Structure your long answers with point, evidence, explanation, and link. And number 3, the time management matrix. Don't overwrite like Alex, and don't rush like Sam. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.